So yeah, this is the cryostat. It has flanges with the different temperature stages. This is the room temperature flange. This is so-called 50K flange, so-called 4K flange. This is the steel flange, cold plate, and mixing chamber. So room temperature has room temperature. It's just for the vacuum and mounting. 50K can have a temperature as low as 38, but I think in your case it will be about 50 really. 4K is 4 Kelvin, but it should be actually below 3.3 to efficiently condense the mixture. Steel can have temperatures from 800 to maybe 1.2 Kelvin, 800 millikelvin to 1200 millikelvin. Cold plate is about 100 millikelvin, let's say from 80 to 100. And mixer, yeah, that's your 10 millikelvin thing, or how much you heat up. And the main parts here, so this is the pulse tube. It starts from that bellows. This is this thing is the spiral, the pulse tube. This is the 4K stage of the pulse tube, or PT2, as some people say. This is the PT1 stage. So PT1 stage cools down to 50 Kelvin. To 50 Kelvin, it has about 10 watts of power. At 4 Kelvin, this is 420, so it has about 2 watts of power, cooling power. Of course, the base has 0 cooling power because that's stable conditions. But then this pulse tube is suspended on a special anti-vibration bellow. That's the standard for all cryostats. Those are the springs that hold it, and the springs are needed because when there is vacuum, this whole thing will lower down. The air pressure will move it down. So of course, all the things which are connected to the pulse tube, including these bobbins for the wiring, and also these things, they will also drop at about 1 centimeter down. These things are the superconducting current leads. Why do we need them? So current leads for the magnet are starting at room temperature. Here are the copper, this is the copper, and it's nickel plated copper tube. That's outer conductor, and there is inner conductor. So there are 3 of these sets which can accommodate 6 wires. And then these wires are also copper. These are copper here. So they conduct heat quite well, down to 50K, because this is thermally connected to the 50K. Now this thing is thermally connected to 4K, and we don't want the thermal conductance between 50K and 4K. So the way to go is to use high TC superconductor. I think it's YBCO on some silver on top of something. So the resistance at room temperature between this and this is about 0.1 ohm, and at millikelvins it's millikelvins. At 4 Kelvin, or actually below 77, here it becomes superconductor, thus not conducting heat but conducting electricity, because you need to conduct here about 100 amperes and in here about 60 amperes, each of them. Right. These are just the supports. This pipe is here support, this is support, this and this as well. But these ones are not supports. These 4 things here are heat switches. And heat switch is a device that conducts heat on command, or rather not conducts it when you want it. These heat switches are so-called gas gap heat switch. So this is a very thin pipe, stainless steel pipe, so it doesn't conduct heat on its own, almost. But it has the copper part here and copper part here. And to be more specific, there are actually 2 copper parts. There's one rod in and there is tube around it. And in between them, there is a helium gas. So when there is a helium gas, in between 2 copper pieces, there is a thermal conduction through the gas. And it conducts heat from here up there. When this thing is being cold, it's actively cooling by the pulse tube. This heat from the lower stages is transferred up. When we are going to use the machine in a dilution refrigerator mode, this thing must be colder than 4 Kelvin. It must be 1 Kelvin. So we don't want heat from the 4 Kelvin to go down. We have to disable the heat transfer at this point. It's not like a heat diode, it's just a conduction. So we have to pump out helium from this gap. And helium is being pumped into the small pumps which are in these places. They are actually covered with this special shield, but this basically an absorption pump. So it has a little bit of a charcoal, and there's a heater on top of it. So if you heat up the heater, if you run the current through it, it will heat up the charcoal and it will release the gas into this gap. So when you heat up the heater, there is gas here and it conducts heat. If there is no heater, at very cold temperatures, the gas gets absorbed into this charcoal absorption pump, and there is no gas, no heat conduction, and heat switch is opened. You apply heater, it conducts. You not apply the voltage, it doesn't conduct heat. As easy as that. And here we have also the heat switches here, because again, mixing chamber will be at room temperature. Like right now it's at room temperature, it will be cooling down to 4 Kelvin as a pole, and then this will be 1 Kelvin, and this will be 10 millikelvin. So we don't need thermal conduction between these. This thing here is a dilution unit. It starts from here. This is the steel, this is the cold plate thing, and this is the mixing chamber. So the mixing chamber itself is this cylinder here, this large one, and the steel chamber is this cylinder here, with the main two bores. I guess you know the operation principle of the dilution refrigerator, technically, but I can remind that in a steady state, when this whole thing is filled with the helium mixture, it's not exactly the mixture, it has two phases. So there are three major phenomena which are quite unique to our world, in which we live, and our universe, and all. That makes this operation possible, operation dilution refrigerator. So one, of course, is that below a certain temperature, the mixture of isotopes of helium-3 and 4, it separates into two types of liquid, two phases. One is which we call helium-rich, and another helium-3 depleted phase. The helium-3 rich phase is like non-super fluid, and that's the thing that we are actually feeding from the top, from this condensing line, thin line that enters the cryostat in here. So it enters it, behind the pulse tube. Here it enters, it goes through this copper thing, which is the small trap. It's just very small, so it's emergency trap, I would say.
Where's the trap?
This cylinder here, this copper cylinder. It's very small. It's thermally connected to 50K, so it is able to trap nitrogen and water, of course. But if there is too much of it, then it will block. Because that other cold trap, which is in the gas tank system, is not perfect. Or if there are small leaks somewhere, or if there is some accident, like nitrogen is running out, then it must save the dilution from blocking. So it's there. Then the helium goes thermalized around the pulse tube and this spiral, this fancy spiral. Then it goes through here, it gets cooled down under the pulse tube again, then there is another spiral here, and here, that's the place here where it enters the steel line. So helium-3 incoming, which is so-called high pressure line, it's relatively high pressure, it's almost half bar in it, absolute. It enters here, and after that, it continues inside the steel pipe all the way down as the capillary. So from here to there, it's a capillary which is inside there. So even if there are leaks inside this thing, for example, there are soldering points, there are some, I don't know, some glue or something, they all stay inside steel, so they don't leak out into the cryostat volume. You don't lose mixture. Of course, you may lose the cooling power, but that's how you see that it's not good unit. But at least you will not lose the mixture. Right, then the helium-3 going down, and well, at the latest point at the steel, there is the main flow impedance, and there, due to the Joule-Thomson effect, it condenses finally, if it was not liquid before that. And after that, the whole thing is basically a giant heat exchanger. Well, giant, big, because this thing, this spiral here, is the so-called continuous heat exchanger. This outer pipe spiral, which is 6 millimeter, 5 millimeter. So that is where cold gas goes up. And inside this, there's a very tiny 1 millimeter pipe, which is like wound in another spiral. And that's where the helium-3, which is hot gas, goes, sorry, not hot gas, hot fluid, it goes down. Rich phase, continuous heat exchanger, and dilute phase goes up, and there's a counterflow continuous heat exchanger. So the hot fluid gets cooled, and cold, well, since it's wasted already, we don't care that it gets hot. Then these things are step heat exchangers. So 1, 2, 3, 4. Step heat exchangers is basically a membrane. On top of the membrane, or so on the bottom of membrane, there is one fluid, and on the other side of the membrane there is another fluid. So one side of membrane this has the hot fluid, and another has the cold one. And again, they are moving different directions, and the idea is the same. The used fluid, which has been already used for the cooling, is cooling down the one which is fresh and coming from up down. This is the mixing chamber. That's where the phase separation takes phase separation takes place. Testing. This thing, that's another phenomenon that is unique to our universe, is that when the helium-3 from the rich phase passes through the phase boundary, it just cannot pass through the phase boundary. It must absorb the heat from somewhere, and it absorbs the heat from the unit bottom, which is not just a plate here. It has very fancy fins inside, which are covered with the sintered silver in order to increase the surface area. They're all in there, and that's quantum phenomenon that when it passes, it needs the energy, so it takes it from there and it cools down this thing, or rather the heat goes from there into the helium, and then it goes into the passing the phase boundary. Another phenomenon which is unique is that the dilute phase, so the helium depleted phase, can have only a certain amount of helium-3. It cannot go to zero in a very dilute way. So it means that if we pump out helium-3 out of the dilute phase, we can never reach zero concentration of helium-3 in it. Its so minimum is about 6%. So the idea is that this whole dilute phase, basically it fills up to the still. And at the still, we pump out helium-3 out of it, utilizing another fancy phenomenon, or fancy property of the helium-3, that the helium-3 gas vapor pressure is much higher than the helium-4 vapor pressure at a given temperature. It's a couple of orders of magnitude more. So mostly all the vapor here consists of helium-3, and we pump it out with the still through this huge line to have as low resistance as possible, partner resistance. And we even need to heat it up, because if you pump it out, it cools down the steel so much that it doesn't evaporate anymore. So there is a steel heater there, and it works the way that we apply heat to this plate, we keep it at 800 millikelvin, and we achieve cooling in here. So we have the heat up in order to achieve cooling. Because we evaporate helium-3 from there, so it means that the amount of helium-3 is decreased, and helium-3 must pass through the phase boundary. That's the quantum phenomenon that is responsible for continuous operation of the fridge. So it goes down, here it pumps out, and it must pass through the phase boundary, and that's how it becomes cold. And this coldness is transferred to your experiment. Yeah, another maybe worth mentioning phenomenon is that helium-3 is diffusing through its superfluid state here, because that's not obvious that you can have a diffusion, or let's say trying to equalize its concentration. So that's another phenomenon that is responsible for operation of the dilution refrigerator.